Assalamu alaikum. Welcome to the next class. So in the previous class we were discussing about the voltage profile of the transmission line from sending end to receiving end in case of a two machine model for different power loading, and in case of a single machine system or a radial system where we have at the sending end one machine, one generator, and the load at the receiving end. So from this we concluded that the voltage variation will be maximum at the middle of the line in case of a two machine system, and in case of a single machine system it will be at the receiving end. So but here we'll be mostly using the two machine model, so we'll be considering this two machine model generally. So keeping this mind, and we have to keep this in mind, that the maximum voltage variation occurs at the middle of the line. Now let us recall that uh, the expression for the real power, which will be generally at receiving or at sending end because of the lossless line. So, or we can say we are including the C as well for a long transmission line. In this case, this real power is calculated as VSER sine of delta divided by Z naught sine of beta A. So, for simplicity, we usually assume that a transmission line will be short, and then A, that is the length of the line, will be small, and beta A will also be small. That will be the beta A, actually the angle of this. So when beta A will be in small, we know that this sine theta by theta will be equal to 1 when theta is close to 0. So we assume that sine of beta A will be close to equal to beta A when both of them are in radians. So where beta A will be equal to omega root of LC into A. Similarly, when we multiply Z naught sine of beta A and then replace the sine of beta A by beta A, it will be equal to Z naught is equal to root of L by C into omega root of LC into A. This is actually the value of beta A. So in that case, this C and C will cancel out. This square root of L and square root of L will be equal to L. This will be equal to omega L into A. Omega L is equal to nothing, but L into A will be the total length of the line, total inductance of the line. So it will be equal to omega L, that is the total reactance of the line. So when we replace this Z naught sine of beta A by X, it will be equal to VR Vs sine of delta divided by X, and when VR is equal to Vs is equal to V, it will be equal to V square by X into sine of delta. We have started from this, and we have ended from a simple relation of real power in terms of voltage, reactance, and delta. So why do we do this? There is a particular reason. In this case, using this is slightly difficult as compared to this, and we have an advantage of using this. We'll see just this. Since sine of beta is less than beta A, Z naught sine of beta A will be simply less than Z naught beta A, which is equal to X. So that means Z naught beta A will be less than X. So dividing both sides by V square sine of delta, it will be equal to V square Z naught sine of beta A divided by V square sine of delta will be less than X divided by V square sine of delta. So when we take the reciprocal of this, it means V square sine of delta divided by Z naught sine of beta will be greater than. This will change its notation. Will be greater than V square sine of delta by X, or V square sine of delta by X will be less than V square sine of delta divided by Z naught sine of beta. So in this case, so that the power considered V square by X sine of delta for the transmission line will be actually less than that of the sine V square sine of delta divided by Z naught sine of beta I for any analysis. So usually we always try to use this type of formula instead of this, which is actually the actual formula including the capacitance, and this is the formula. In this case we are actually neglecting the capacitance. So since this is less than this, when we analyze the system for this case, it will automatically, or when we design the system for this case, it will automatically be designed for this. So we can say this is the worst case condition for our system. So when we design it for this case, we are designing it for worst case condition, it will be automatically designed for this. So this will be good for us because this is the simple relation, and it is also taking care of the system whose actual relation is this. So from now on, we mostly will be using this type of relation in this relation instead of this relation. Now let us try to do the uh, derive the power flow formula in a two machine model using the same condition, that is worst case condition. So worst case condition means we are neglecting the capacitance, we are assuming for the time being, even if it's a long transmission line, we are not taking care of the capacitance. So here I have divided this reactance into two parts, keeping one at the left side, that's x by 2, on the right side x by 2, and we assume that m is the midpoint of the transmission line. So the current here will flow through here, and in this case we are assuming one more thing, that Vs is equal to Vr, that is equal to V. Capacitance is neglected, as I have told you. So using the KVL in this loop, Vs is equal to Vr plus Jix. Generally, power factor is lagging, and phasor diagram will be as follows, like this. So the phasor diagram for this case, we are assuming this Vr to be the reference and IR to be lagging to this system. So we are adding this phasor to this VR. Definitely this phasor will be leading to this current by 90 degree because of this Jx. And we know that voltage across inductance, because this is the voltage across inductance, this phasor will be leading to this current by 90 degrees. So we have to take care of that. This will be 90 degrees leading to this, and we have to add to this VR, and we'll get the Vs. This will be the Vs. So this is the general phasor diagram of any system when the power factor is lagging. But we need to actually find out the system where the power factor is where this, in this case you can see Vs is greater than Vr. Here we have to draw the this phasor diagram in which this Vs is equal to Vr. Assume that will be equal to V. So in that case, as we know that when Vs is equal to Vr, this is only possible when power factor is leading. We have discussed this in the power system first, that this voltage regulation will be leading when power factor will be leading. So in this case I have drawn this leading to this, and in such a way, because when the power factor is lagging, voltage regulation will always be positive, and power factor is leading, voltage regulation can be positive, negative, as well as zero. But we have to draw this in such a way so that voltage regulation is zero, or we can say Vs is equal to Vr. So I have managed somehow this Vs should be equal to Vr. So in this case I draw IR leading to this Vr, or you can simply draw first Vs and then Vr in such a way so that they are equal, and then draw this Jix, because definitely this voltage drop will be the difference of these voltages. So this voltage drop will always be, we can say, the third side of this triangle. So then from this side you have to draw this so that it is perpendicular and lagging to this by 90 degree. So let us say it comes over here. Now this is actually the same diagram, but I have tilted it towards the left side so that you can see I have rotated it like this, so that this Jx comes to be horizontal as compared to this. So this is Vr, this is Vs, this is I, so this is theta power factor angle, and this whole angle is delta, that's also shown over here, and this is the Jix. So here again Vs is equal to Vr is equal to, let us say, V. So I have made this here again because I need to derive something from this triangle, from this whole triangle. Let us assume we have two triangles, this OMB and OMA. These two are right angle triangles because this current is perpendicular to this current, and I have extended this to point M. Let's say this is some point M. So since this current is perpendicular, this will also be 90 degrees, this will also be 90 degrees. So from this, angle OMB is equal to angle OMA, both 90 degrees, that is these two angles OMB and OMA 90 degrees. Vs is equal to Vr is equal to V. Vs is equal to Vr, that is equal to V. It is given from this assumption, to machine model assumption, and OM is equal to OM is the common side. OM is equal to OM. Therefore, by right hypotenuse side, that means in a right angle triangle, if two triangles are right angle triangle, their right angle is same, that has to be same. Hypotenuse is same, that is Vs and Vr is same, and any side will be same. That means that triangle will be, these two triangles will be congruent. That means triangle OMB will be congruent to triangle OMA. So in that And this is the case because of the corresponding parts of the corresponding triangles. Then angle 1 will be equal to angle 2 and AM will be equal to BM. Since angle 1 plus angle 2 is equal to delta, then angle 1 is equal to angle 2 will be equal to delta by 2. Similarly, BM is equal to AM and summation of these will be equal to IX magnitude only. That means AM is equal to BM is equal to IX by 2. That is what I have written over here. Angle 1 is equal to angle 2 is equal to delta by 2, corresponding parts of the corresponding triangle, and BM is equal to AM is equal to IX by 2. That is again the same. So from here you can see then this M is the midpoint of the transmission line. That this M, which I have already assumed over here, this M actually represents this M represents this point of the transmission line. Otherwise, in the earlier case, it was not without this derivation. And hence Vm is the midpoint voltage, and Vm, that is this voltage from this point to this point, will be the voltage at the middle of the line. Now the real power at receiving end will be equal to PR is equal to VR, IR cos of theta R, VR is equal to V, IR is equal to I, and cos of theta R is equal to cos of delta by 2. So we'll first derive what will be the value of I. From this triangle, that is this AMO, this VR sine of delta will be equal to IX by 2, that is this side AM. VR sine of delta or V sine of delta by 2 will be equal to this AM, that is IX by 2. That's what I have written over here. So V sine of delta by 2 will be equal to IX by 2. That means I will be equal to twice V sine delta by 2 divided by X. So therefore P is equal to V into twice V sine of delta by 2, that's in place of I, and power factor will be cos of delta by 2, that's VR IR cos of theta. So when you multiply it, it will be equal to twice V square by X, sine of delta by 2 cos of delta by 2. So it will be equal to, then this twice sine of delta by 2 cos of delta by 2 will be equal to sine of delta. So it will be equal to V square by X. Again the same result which we have derived just before, where I assume that it is a short transmission line. Similarly, Q is equal to Vi sine of delta by 2. That's V twice V sine of delta by 2 by X into sine of delta by 2. So combining these two, sine of delta by 2, sine of delta by 2, it will be equal to 1 minus cos of delta. That will be twice sine square delta by 2. So this will be the Q. This is again an important result, because in this case you will see that when P is changed, Q should also be changed to keep the voltage in limit. So when P is changed from this to this, Q has to be changed like this. Otherwise, this VS and VR will not be same. So we can say this P and Q are dependent on each other. When P changes, Q automatically has to change. Otherwise, this voltage limit will not be there. So to increase the real power, one more thing from here. Real power P, delta has to be increased. This we know because this P will be equal to V square by X sine of delta. One more thing, for a fixed value of X, when delta is increased, current I will increase, which increases Jx. Or we can, yes, I'll go directly from this. When delta increases, what will happen to this I? I will increase twice V by X sine of delta by 2. Delta increases, this I increases. When I increases, this Jx increases. That means delta increases, they become apart. This is the first triangle which we have just derived, which we have just drawn. That is, let's say this is this triangle. So when delta increases, they definitely goes apart from here. It will be here and it will be here, and delta will be more. That's what I have shown over here. This is the previous case, this one is the previous case. Now delta increases from here to here, and now definitely this voltage phasor will be more as compared to this, because I increases because of this relation, and this X is constant. Or in other words, definitely this voltage phasor will be greater than this voltage phasor, because this voltage phasor has to increase to complete this triangle. So delta 2 is greater than delta 1, I2 will also be greater than I1 I2x will be greater than I1x, that is this. Now this current component, we can say this I1 is greater than less than I2. Now the current component which is in phase with this will be actually uh, responsible for the real power. This current component has a component which is in phase with this VR, that will be also responsible for the real power. The current component along the voltage, that is I cos of delta by 2, that is this I cos of delta by 2, whose product is the power, whose product with voltage should have been is power, keeps on increasing. It will keep on increasing, reach the maximum value. It will reach a maximum value and then decreases to 0 when delta is equal to 90. So maximum value when delta 1 is equal to 90 degree. When delta is 90 degree, delta by 2 will be equal to 45 degrees and it will be equal to I by root 2. And then when delta is equal to 180 degree, this will be equal to 90 degree, it will be equal to 0. So this when delta increases, current component along the voltage will increase, reach the maximum value and then decrease to 0 at the delta's value. You can see at this delta, when delta is equal to 180 degrees, current will definitely be very high, because in this case this Vs plus Vr, it will be same as that of the Vx. Their summation will be equal to Vx, sorry, I into x, but there will not be any component of the current which is in phase with this Vr. So that's why when delta is equal to 180 degrees, it will be equal to 0. Now this is very important, you need to be very attentive for this case. The variation of the in phase and the quadrature component of the line current I with respect to VR as delta is increased from 0 to 180 degrees, that is delta by 2, is varied from 0 to 90 degrees, is shown over here. Actually I have shown all the voltage phasors and current phasors here, but I will first show one of the voltage phasor and current in this case. Let us say this is here I have not shown, this is the phasor of VR. I should have shown the phasor of Vs, even if it would have been dotted, it would have slightly clear to you, but you should try to make it like this. This is Vs over here. This is Vs and this is the current. This is actually the half of this triangle, that is this. I'm only drawing this triangle from here to here to here, or AMO, I'm drawing only this. I'm showing this phasor and current phasor, not this phasor. Now coming to this, let us say this angle is 30 degrees for this case. That means delta by 2 is 30 degrees. So this is Vs, this is current. Now when we break this I2 into two components, one component which is in phase with this uh, voltage, another component is in quadrature R, which is perpendicular to this voltage. This is the cos component, this is the sine component. So this component will be equal to I2 cos of delta 2 and this component will be I2 sine of delta 2. This is actually I2 will be over here. That is what I am drawing this with respect to this, and V2 is 30. V2 is when we are having 60 degree with respect to Vs and 30 degree with respect to current. The delta by 2 is 30 degrees. Now when we have a multiplication of this voltage phasor and the current component along with this, it will result in the power. Let us say that power has been represented by this dot. So this dot has been represented over here. You can see this is the 30 degree voltage phasor and this is its current, corresponding current. When we multiply this voltage by this quadrature component of the current, we will get the reactive power. So let us start with the 15 degrees. When 15 degrees is the angle between this voltage and current, that is delta by 2 is delta by 2 is equal to 15 degrees. In this case, this is the voltage phasor, this is the current phasor, and from here to here, when we break it into, or when we draw on the cos component on this case, you will get this will be the, from here to here, this will be the current component in phase with this voltage. So taking the multiplication of this V and I am assuming that value is equal to this, and I am taking this point to be equal to the real power. And the second point which I have discussed over here, which comes out to be this. And the third point, when V3 is at 45 degrees from this axis, or from the current, or delta by 2 is equal to 45 degrees, you can see in this case this current corresponding to this 45 will be equal to I3. It has to increase So in that case, the component which is in phase with the voltage will be this, and this is the quadrature component which is actually responsible for the reactive power. So this point will give us the real power. Real power, that is the multiplication of this V3 and the current component of this I3 along this V3. So this point will be similarly when V4 is the voltage which is at a 60 degree from this current, or delta by 2 is equal to 60 degree. In that case, you can see this is I4, it has to increase, and when we draw the perpendicular from this I4 to this V4, I4 is this, from this to this is the perpendicular, and this will be the cos component. Now it will decrease because you'll see that the cos component, this perpendicular, will go on increasing, but this in phase with this voltage will now decrease, and the point of this current and this voltage, let us say that is this. And similarly for V5 is equal to 75 degree, it will be like this. When we join, this is the locus of the real power. This is the locus of the real power in the phasor diagrams that started from 0, reaches to a maximum value, and then goes again to 0. Similarly, by the similar analysis, the reactive power will change from this point to this point, which I have shown with the red. It will be 0 when delta is equal to 0, or delta by 2 will also be equal to 0, and it will have a maximum value when delta is equal to 180 degree, or delta by 2 is equal to 90 degrees. So this is how this P and Q will vary with respect to when delta varies from 0 to 180 degrees, or when delta by 2 varies from 0 to 90 degrees. I think I will stop over here. Thank you.